Okay. Hi, everyone. Thanks for joining today. So today, it's my pleasure to welcome Percy Liang, who's an associate professor of computer science at Stanford. His research spans many topics, from machine learning to natural language processing, including robustness, interpretability, semantics, and reasoning. And he's won numerous awards, including the Presidential Early Career Award for Scientists and Engineers, the IJCAI Computers and Thought Award, a Sloan Research Fellowship, among others. And today he's going to be talking about some of the work he's been doing on learning to fix programs. So yeah, thanks for joining us, Percy, and I'll hand it over to you whenever you're ready.
Okay, great. Thanks for the introduction, Osbert, and the invitation. I assume everyone can see my screen and hear me just fine. So let me start with some context. So for a long time, I've been interested in program synthesis ever since grad school, either from examples or natural language through the moniker of semantic parsing. And I think as a field, we're pretty good already at synthesizing small programs. And the main challenge has, for me at least, has always been how do you scale up to something more ambitious? And I think we have made progress, but somehow it never really felt like the right problem in the limit, because would you really be synthesizing like 1 million line programs kind of from scratch? So then we started thinking a lot more about other kind of contracts and in particular editing programs where you already have a large program and you want to change it for some reason. And this talk, I'm going to focus on program repair, which is the reason you want to change it is because your original program is broken and you want to fix it. So this is all going to be work done with my student, Michi. And I believe Michi might be joining. So in case you have any questions, you might be able to answer them in the chat.
Yeah, so I'm here. So yeah, feel free to leave any comments on the chat.
Okay, great. Thanks, Michi. All right, so let's jump in. By the way, Osbert, I have an hour. Is that right? Or
yeah,
maybe 15 minutes. I'll try to leave time.
Yeah, we can run over if you have time after, but it's an hour.
Okay. Well, please feel free to interrupt with any questions, either in the chat or just holler. We can try to make, it's always nice to make these Zoom meetings a little bit more interactive than they otherwise would be. So let's jump in. So there's actually a much simpler way to motivate program repair. Programmers make bugs and spend a lot of time fixing them. Time is money. So we want to somehow be able to do this more automatically. So in this talk, I'm going to focus on two different approaches to doing program repair. The first one leverages compiler feedback, or more generally, feedback from some sort of executor. And the second one is leverages, also a compiler, but uses it in a different way in conjunction with unlabeled data. So a big theme of both of these is what can you do with just unlabeled code that you find lying around and a compiler? So you have two things. What can you do to do program repair? We're going to be fairly low tech when it comes to kind of actual models of programs. I think all that great work is kind of complementary. This is more focusing on more of the kind of the systems, how the components and the data kind of plumb together. So let's dive into the first project. So this is the ICML paper from last year with Michi, and it's called Doctor Repair. So the motivation is learning from feedback. So when you write code, you write some code, unless you're, for most people, it doesn't work the first time. But fortunately, you get some feedback from the compiler, from the executor, and then you look at that feedback and you say, aha, that's what I did wrong, and I go and fix my code. And so we kind of want to take that intuition and try to operationalize it. And this shows up in a different, a bunch of other places, this idea of learning from feedback, like if you're editing, you have someone give you comments about your writing, and then you go fix it. As a concrete motivating example, let's take a look at this C program, which is broken. If you try to stick it into a C compiler, it will generate this error message. We're going to think about this, everything is like kind of a string. So there's no real types, they're just tokens. And what this feedback intuitively is pretty helpful. It tells you on line 9, there's this A, which is doing something weird. And then if you're a programmer, you look at this A and you follow it and you say, aha, well, this A has been defined as a character, but I'm trying to get its size and that doesn't work. So what you like to do is fix it by turning this character into a string. And so that's what the doctor repair system, which I'm going to describe, will do. It takes a broken program, it takes diagnostic feedback, and it generates, localizes the line to fix and repairs that line. So notice that the line that I'm fixing is not necessarily the line that is reported in the compiler. So there's two challenges I'm going to have to tackle. One is how do you model the relationship between the source code and the compiler message? And the second one is how do you get data to solve this problem? So for the first point on the modeling thing, we're going to introduce this idea of a program feedback graph, which I'll describe later. And the second point, we're going to actually show how you can use unlabeled data and do self-supervised learning to train up a model for program repair. So let's begin with the program feedback graph. So we have code, we have the compiler error, and we need some way of for defining a neural model that kind of connects these two up. So what we're going to do is we're going to define this program feedback graph. And the way it works is we first identify various tokens like identifiers, data types, operators, and these arguments, which are things in quotes. And we're going to call them the nodes of a graph. And then we're going to connect them all up as follows. So we're just going to connect all the instances of A together. So it's going to be one giant complete graph and all the instances of char together. So really, I mean, it's a graph, but it's really a set of equivalence classes. And these edges correspond to semantic approximate notion of semantic correspondence. So we're assuming that all identifiers kind of have the same semantics, which is obviously not true, but true enough for present purposes. So more details about the actual neural model that's built on top of the graph. So here's an example. Here's 3 lines of source code. Each line is a sequence of tokens. And we also have the compiler message, which has the line number that's mentioned, as well as the sequence of tokens for the message. So this is fairly kind of standard machinery in NLP. You use a bidirectional LSTM to provide contextual encodings, so a vector for each token, which depends on a kind of a soft neighborhood of that vector. And then we're going to do graph attention. And this is where the graph is going to come into place. So remember, the graph connects tokens with the same kind of name. And so we're doing this kind of message passing where each of these tokens, which are connected to this node in the graph, pass messages. And the aggregation is this multi-head attention, which I won't get into details, but it's some module that produces another vector that depends on the vectors that are neighbors of this node. So you do this a few times, and at the end of the day, you get for each token, for example, character, you get some vector here that depends not only on the local context, so for example, the things around character, but also the global context, in which case this would be, I guess remember there was a instance of the word char in the compiler message, so it would kind of pass messages to the compiler as well. And finally, you do another layer of LSTMs, and you get a vector that represents each line. So every line will have a vector that encodes something about the relationship between that line and kind of the rest of the program and the compiler message. And now from there, you can predict the line number where you think the error is happening on, as well as using a pointer generator network to actually do the repair, which means generate the line of the sequence of tokens that is meant to replace the line that was localized. Okay, so I went this over fairly fast, but I think the details aren't so important. I just want to maybe summarize the high level bit, which is that at the end of the day, we have source code and we have a compiler message. We do the kind of normal neural net thing of contextual word embeddings. But in addition, we stick in this graph network that allows you to take into account the program feedback graph, and then some more kind of local initialization, and then you generate the line that you want to repair and the actual line that you want to the actual sequence of tokens that you want to replace the original line with. Okay, maybe I'll pause a little bit in case there's questions about what's going on here.
Yeah, Percy, I'll bite if you want.
Sure.
So it seems like this is like a lot of the other program repair research I've seen, basically working with a purely syntactic view of what the program is doing. Is that accurate?
Yeah, this is very syntactic.
Yeah. So I believe you can get part of the way there. I believe you can accomplish some nice software engineering tasks doing this. But at the end of the day, do you think you're going to have to build a more semantically rich model of the program if you really want to start making some major inroads into these kind of problems? Or do you think it's all this kind of surface syntactic stuff, and if you dump a deep enough neural network on it, it'll figure everything out and fix it all for us?
Yeah, I knew this question was going to come up. That's why I said at the very beginning that this talk is going to be very low tech when it comes to the representation of programs. I think
so far
it
you've
comes.
Delivered.
Sorry.
I said, so far you've delivered.
Yeah. So, thanks. So it depends on what kind of things you're trying to repair. Most of the errors that we're talking about here are fairly syntax and superficial, where you could probably do in your sleep. I think when it comes to really tricky bugs, that let's say you're trying to debug something like on a program with concurrency, then yeah, there's no way this is going to work. Like you need to understand the semantics and the invariance and all that stuff. So all that's, I think another way this is kind of less this step one. I think I want to move past this pretty quickly. I think if you have a better semantic model, I think you can drop it in, and we could kind of leverage that as well. I think some of the applications we'll show you later are you'll see that the syntactic view is actually reasonable. We'll show you how we're fixing like kind of beginner program errors, which I don't think you need that much semantics for kind of basic things. And also like in another application is program synthesis, where it's like you don't have to get it exactly right. You just have to have good guesses, and maybe some sort of syntactic thing can give you good guesses.
Sure. I mean, I could derail the talk arbitrarily at this point. Why don't you go ahead and I'll derail it later? But I guess the real question is, the deep question is going to be, why are you doing this research?
Okay.
Don't you have bigger aspirations?
How
right?
about you
So you can see where this is going to go, right?
Let's derail this later, okay?
Yeah, exactly.
I'll try to go fast so we can have more time for derailing.
Okay, see ya.
Okay. Let's see. Maybe Michi can answer the questions in the chat while I go on, so we can get to the fun stuff. Okay, so the second part, which hopefully is sidesteps a lot of modern concerns, is like where does the data come from? And a lot of program repair requires these labeled data sets of bad code, good code, and that's just really not scalable. And the question is, there's so much code out there. On GitHub, there's 30 million repos, even code forces for programming. Programs have, contest programs have, 1 million submissions. So how can we leverage them? Surely we have to be able to learn something about them. So here's a really simple idea. It's not new. The new part is, I guess we're incorporating the feedback, but it's fairly basic. The idea is you get some working code, and then you design some heuristic perturbations to screw it up. And then now that's your training data. You have the screwed up code. You run through the compiler, you get feedback. and you have the correct code. So this is kind of like a noisy autoencoder, except for the fact that you have feedback from your compiler, which gives you additional piece of information. And then you just train on this. You can do this for as much code as you want. We had some examples in C++. So we gathered 300K code snippets from code forces. We looked at common types of errors, and we designed kind of these simple perturbation modules. Like if you want to screw up the syntax, try to delete operators. If you want to try to change, like have type errors, then go after types and so on. Fairly simple but heuristic. And then to generate data, you start with working code. You sample a bunch of these perturbations, and then you just apply them. You change the type, you replace this identifier, and then you remove the semicolon, for example, up to 5 perturbations. So then you prepare this training. So then you just have your training data, broken code, feedback, and you want to map it to fixed code, and you just train on this data. So we looked at 2 applications. The deep fixed data set is student-written programs for some programming course, some of which are broken. For example, this one, it's missing a brace. And how well do we do on this? Here is an example of what a Dr. Repair Our System is able to do. It takes this code, it runs it, it sees like, oh, I is undeclared. So it goes to and it fixes this by adding the definition of I here. And then it runs the compiler again. It sees, oh, well, line 12 is broken, and adds a semicolon. And then it works. So here's a successful case. Overall, there's some previous work that doesn't use compiler messages. And the main gain that we're getting is using compiler messages, which is maybe not surprising, but I guess that's kind of the point, is that, well, we have this compiler as a valuable asset here. Why not use it as feedback into the model itself? And it's not, and it's important that it's not just like the line number, because line number doesn't tell you where to go and how to fix it. It's also crucially the error message that comes, which is just a string that you have to interpret. And then, so the compiler message is important, and both graph, the use of the program graph and pre-training are useful. So we get pretty reasonable results here. The second application, which I alluded to earlier, is program synthesis from natural language. So this is Spock is a data set that we put out 2 years ago. It's a fairly kind of, well, I wouldn't say it's simple, because I think accuracies are still pretty low. So I think it's still an open challenge, but it looks simple. It's basically line by line. You have pseudocode written by crowd workers mapping to real code. And the goal is to translate the pseudocode into real code. And the programs are like 20 lines long, so it's not of C code, so it's not that trivial. So previous work used the model to generate candidates for each line, and then there's some best first search over different combinations of the candidates. And this is kind of a little bit, brute force. It's kind of unguided. It's just looking at different combinations. And sometimes the candidates on the list aren't even enough. So we basically said, well, let's just use Dr. Repair here. At any point in the search, we can run the candidate program and see if it compiles. If it doesn't compile, then it generates a message. We feed that into a model, and then we get a repaired suggestion, and we add that to the set of candidates and rescore and continue best first search. So we're using Dr. Repair in the inner loop of the search procedure. And the results are pretty promising. So
just to understand the data set, is it like, is there a one-to-one correspondence in the lines in the natural language and the code?
Yeah, so this is one-to-one between natural language and code.
Okay, and then Dr. Repair is also kind of applying line by line, and that's what makes it possible. Is that?
Yeah, exactly.
Okay, got it.
Yeah. So the results are pretty reasonable. When we put out the Spock paper, our best number was 34.2, and using this repair with compiler feedback, we're up to 37.6. I think there are some better numbers, ones that look at more of the type information, So richer semantics does help. So maybe that'll make Martin happy. So maybe let's see, just some quick analysis. So we broke up the errors by different types of compiler error messages. For the lines that require reasoning about multiple lines of code, we saw that the graph, adding the program graph produced the most number of gains. And for the cases where there were infrequent compiler messages, that's where the pre-training was really helpful, because pre-training, again, is meant to capture kind of the long tail of different types of patterns that you see. So this kind of checked out in terms of it made sense. Okay, so just to summarize this section, I think the top level bit is that error messages and feedback, I think, is a useful signal to guide code repair. I think it's, in some sense, it's kind of intuitive and obvious, but exactly how to incorporate that feedback into a system maybe requires a little bit more thought. So the program feedback graph allows you to do kind of this reasoning over different tokens, and the unlabeled code, which is a theme that's going to come back again in the next part of the talk, I think is a powerful tool that allows you to leverage a lot of code online and do useful things like train program repair systems. Okay, maybe I'll pause again in case there's other questions.
Yeah, I had one question. So this it relies pretty heavily on the compiler to work, right? Because you need some kind of a checker that already knows there's something wrong, and then you can go back and figure out maybe more specifically what was wrong. So I'm wondering if you have any, do you think these techniques generalize beyond that, or is the main point showing that if you have this kind of oracle, then you can get this benefit out of it?
So all this work definitely strongly leverages the compiler. We've been exploring with Michi some other ideas, not in more the natural language space, where you don't have something akin to a compiler. And there you might have, for example, a language model, and you want to do, let's say, grammar correction. We can show that you can finagle a language model into acting like a kind of approximate critic as well. So I think any sort of feedback could potentially be useful. And actually, in some ways, I think the system is pretty tolerant to, even if the compiler were kind of erroneous, I think it's more the qualitative aspect of what is the information that's in strings, like the natural language that's being written down, that can be used to inform what I should do next in my repair. So think about it as almost like hints. And there are cases where, for example, linter errors, are those real errors? I don't know. And I think even in those cases, you might imagine those being of varying levels of utility. Okay, let me go on. So the next part is called break it, fix it, or BFI. And this is going to work in under submission right now. So the problem is we're going to use the compiler and unlabeled data as before, but we're going to use it in a different way. And so the idea is that we have a compiler, and the compiler, what it does is it's a critic. It takes an input and says, is it good or bad? But what we really want is a fixer that not just is that guy that only kind of is a naysayer and says, gives a critical feedback, but actually is constructive and can take a broken piece of code and turn it into something that works. And the way we're going to do this is use unlabeled data to kind of connect the two up. So we call this framework kind of critic to fixer. So you have something that only gives you a binary yes or no to something that actually can do kind of fixing. This occurs in a bunch of other examples outside program repair, for example, molecule design or assay editing. So this is hard because usually if you want a fixer, you need examples, and these are expensive. So how can you use unlabeled data? So here is, well, I guess this is the same slide, but basically just to repeat again. So we have unlabeled data, unlabeled inputs, and we have a critic, and we want to produce a fixer. So our starting point is kind of previous methods. So there are already actually a lot of methods that use unlabeled data. And typically what you do is, well, you have good code and you say, well, I need some bad code. So what do? You just make up some perturbations that screw up the code, because screwing up code is pretty easy. And you just generate some broken code. And now you have training examples of good code, of bad code, good code pairs. The main problem here is that there's a distribution mismatch. For example, take this correct piece of code. A synthetic perturbation might just delete this parentheses. So it's like, okay, yeah, sure, that's an error. But humans are more likely to actual miss kind of nested parentheses at the end than kind of random parentheses. And so there's a kind of a distribution mismatch. And we know that whenever you have distribution mismatch and you train a model in ML, you're going to see accuracy drops. So what can you do to mitigate this distribution mismatch between a real bad code? I mean that I don't mean really bad code. I mean bad code that is real, found in the wild, versus bad code that you synthesize. So here's the idea behind break it, fix it. We're going to train a breaker that generates realistic bad code. And this idea is kind of inspired by back translation and unsupervised machine translation, which is another way to synthesize data. And we're going to train the breaker and the fixer on this unlabeled data and use a critic to generate kind of more good examples. And this is kind of related to ideas of self-training. So here's how it works in one slide. So suppose you have a fixer, a preliminary fixer. So this BP is going to be an iterative algorithm. So how can I improve this fixer? So you take your bad code, and you know it's bad because you have a critic. So you can run the compiler and say, okay, this has an error. So you take some bad code and you apply the fixer. And you don't know if the fixer worked, but you have the critic. So the critic can tell you whether the fixer succeeded or not. And if it succeeds, then you keep that code. So now you have examples of real bad code and the fixed code. And now you have these examples, you train the breaker. The breaker takes this input fixed code and tries to produce bad code. But now the key thing is that the distribution it's training on is it targets these type of bad code that actually occurs. So it's trying to mimic the type of bad code that you see on GitHub as opposed to things that are synthesized. Okay, so now you have a breaker. You take your good code, which you know because you have the critic, and you apply the breaker. And the breaker might not be perfect, but you have the critic again, and you can keep the output of the breaker if it's actually broken, as deemed by the critic. And so now that generates additional pairs of broken code and good code. And now you take all this data and you train a fixer. So that's one iteration of Beefy. And now you have a fixer, you can go through this process again. So the idea is that you're trying to train a fixer, and you need the fixer to be trained on kind of realistic bad code. And at the same time, you're training this breaker to generate realistic bad code. And so there's kind of a virtuous cycle where these two, the better these two become, the better the data become, and things just improve from there.
I have a quick question. Do you have ground truth fixed code, or are you just assuming that the initial fixer on the real bad code is correct?
Yeah, so something I'm glossing over is that the notion of what it means to fix is kind of not well defined. So operationally, we think of it as something that passes the critic, but is within some edit distance. So obviously that's an imperfect definition, but I guess that's kind of intrinsic to the problem because often there's multiple ways of fixing a piece of code.
Okay, got it.
Okay, so so let's just compare with back translation for some of those of you who are familiar with it. So back translation, this idea in machine translation, which has been very successful, is essentially the same, except for there's no critic. And because there's no critic, they train on examples of only the I guess the bad code and the possibly fixed code, and not the good and broken code, because they don't. Sorry, the other way around. They train only on this data, but not this data, because they don't necessarily trust that the output is going to be good. So in machine translation, the bad code stands for some language, and the good code stands for some other foreign language. So, and in some sense, the main difference is that because we're in program synthesis land, we actually have this critic, which is something that you don't have when you're doing machine translation. So we can leverage it. Okay, so there's also another baseline, which you might kind of be natural to think about, is you take some bad code and you only apply the fixer, but you don't train a breaker. So this is called fixer only. So we gathered a data set, a scraped GitHub for Python programs, and it's about 3 million Python codes, programs. And most of GitHub is good programs, but people do check in code that just doesn't even parse. And actually, some of these I think are Python 2, Python 3 problems. But the critic is basically the AST parser. So obviously not very far away from a kind of real program semantics, but it's just kind of a good initial step. So what we do is we train a standard C2C transformer, and we generated a synthetic paired data to kind of similar how we were doing with doctor repair, by just having a few heuristics of dropping and inserting tokens. And then we train a fixer. So that fixer is initialization into 2 rounds of BFE training. Okay, so let's see what happens on this GitHub Python data set. So initially, we get 63% in terms of success rate for fixing the program, which is, and this is based on kind of the standard paradigm. You take some good code, you generate some synthetic code using heuristics, and then you just train a model. And it doesn't do very well, mostly because the distribution is just not good. And we show that if we add fixer only, so we're incorporating real bad code, that already improves things quite a bit. And then using the full BFE over multiple iterations, it reaches 93%, which is quite a bit higher than the initial model. So BFE actually is quite successful in turning this essentially naive fixer, almost like a denoising autoencoder, into something that's actually quite usable. We then looked at the effect of the breaker. So the gap between fixer only and the breaker is quite substantial. And also, here's some examples of breaker outputs. So we train a breaker that takes good code and tries to screw it up. And you see that it generates fairly realistic outputs. So this one is using this kind of obsolete usage of raise, where you have a comma instead of parentheses. And this one deletes a parenthesis at the end, which is typical of errors that you see in the wild. Comparing with back translation, which remember is we're not using the critic, and we're not training on the real bad code. So the gap is quite a bit, from 80% to 93%. So use of the critic is helpful. Let's see, how does a fixer adapt over time. So on some categories of errors, for example, unbalanced parentheses and missing comma, where the types of errors that you see in practice are actually, it's like one token, and the synthetic perturbations might not see it that often, but it will eventually, get it. And you see that the gains are, reasonable. You go from like 94 to 97-ish. But if you look at the types of errors that occur with very, very small probability. So for example, in some cases, like the real bad code, you have an extra parenthesis, pair here, which is something that just naive generations you can't, is hard to get because you have to synchronize on 2 tokens. On these type of errors, the gap is much larger, from 13%, for example, to 87%. So this suggests that Beefy, by training the breaker, it's really able to kind of adapt to these types of errors that you wouldn't be able to kind of see otherwise or synthesize without a model. So here are some more examples of fixer outputs. So initially, the initial fixer, here's some bad code which the indentation is messed up. This error needs to be indented. And one thing that about, I mean, this is a detail, but I think in order for this example to make sense, I have to explain it. So the way that programs here are encoded is that when you indent and you have a new line, then things are kind of auto-indented, and you have to dedent to explicitly. So by just inserting an indent here, then everything gets indented. And so that actually doesn't work. And you actually need to kind of remove this extra indent for this to work. So it's a kind of a 2-token change, which is kind of much harder to get with the initial fixture, but Beefy was able to do. So there's the deep fix data set, which remember was the student programs from a programming course. And on this data set, the setup is basically a scheme, so I'll skip over that. Here, the doctor repair was our initial result from last time, and this already outperforms past work by quite a bit. And then using Beefy to get a more realistic distribution of errors, we're able to further improve this from 66 to 72%. So there's a state of the art on this data set. Okay, so to take final takeaways here. So Beefy enables, the key point is that it's able to create realistic data using the critic unlabeled data. So you have most of the data out there is actually good. So bad data is actually kind of hard to come by. So you kind of need to sometimes synthesize it. But if you just naively synthesize it, then it generates a distribution mismatch. So if you train a model, the breaker to synthesize it, then it works pretty well. And it's able to adapt to these real code distributions without kind of manual effort. The initial synthetic perturbations were very, very simple. And even in the deep fix case where we actually had hand-designed heuristics in our previous, in our ICML paper from last year, Beefy was still able to improve on top of that. So, which suggests that the automation is not just for, not just for fun. And more generally, the idea of using a fixer, learning a fixer from this critic and unlabeled data, how do you do a critic to fixer, I think is a interesting and general paradigm to explore. And finally, just to wrap up before we take questions, this work, I think the heart of this work is a very kind of ML perspective, I would say. You have this unlabeled code flying around, you have this compiler, and you're asking the question, if I want to be really lazy, what can I do? How can I leverage this to generate something, interesting? And we shot kind of 2 examples of how to harness this data in a kind of a new way. One is to let the compiler generate feedback, and the other is to use a compiler to kind of curate this kind of more realistic data distribution to train a fixer from a critic. So this might be interesting to discuss. I'd be curious to hear what people think about this idea of using these kind of really rough but very cheaply available data and tools to bring to bear on program problems. With that, so thanks for your attention, and thanks to funding sources.
Okay. Thanks, Percy, for the great talk. And yeah, I guess we can, yeah, if there are any questions, then ask.
I got a comment and a question if you want, Osbert.
Yeah, go for it.
So first, so Fanlong's profit system, which used a machine learning model to rank patches, had a similar idea of applying the patch patterns to correct code to generate incorrect code to be able to train the model on negative examples, because there weren't, as you pointed out, a lot of negative examples of bad code available easily. So that's how he did that. That was a profit system back in 2016. Next question is, maybe this went by pretty quickly. Did you verify that the patches that you were applying actually were the right patch, or did they just get you past the compiler?
Yeah, I mean, Michi maybe can say a little bit more since you looked at the data a bit more carefully. So the main thing is we had, what was it, the edit. So we were deeming it to be successful was if it was within edit distance 4. Anecdotally, it seemed like it was kind of doing the right thing. It wasn't like it was kind of cheating in the system, somehow. I think, I think it's a good point, and I think if you were doing something more akin to reinforcement learning, I would be much more worried, because you can kind of do reward hacking as like, I'm just going to do some adversary perturbation to fool the compiler. But because each time the system is actually it's pretty grounded in the types of real code that you find on GitHub, either bad or good. It stays pretty close to the types of things that you would see. But it is something that is to be careful of.
Yeah, let me give you. I mean, you may know this. I don't know. But back in the software engineering community was doing kind of some of this program repair research, right? And one of their big famous systems turned out to have this problem that they said they were fixing all the bugs. And when you went and looked at the fixes, essentially all of them went in, and in using various clever code manipulation strategies, simply deleted the code that was given them a bad result. So
yeah,
you might want to go and take a little closer look at what's going on here, just to be sure you're not sort of falling into a similar pitfall.
Yeah. So definitely nothing that blatant. We have noticed that, and it's not.
No. So the surface manifestation wasn't blatant at all. It was some complicated ass thing that when you analyzed it in the context of the system, what it boiled down to was deleting the code. The code was still there, it just never executed.
Right. Yeah, that's a good point.
Maybe you could deal with that by generating some test cases for valid code, breaking it, fixing it, and then verifying the test cases still hold.
This particular piece of research worked by isolating the bad test cases and deleting the code that was responsible for generating the bad result on the test cases. So it was a test case based approach.
Yeah, but the test cases could be useful in this case to at least have some sort of sanity check on the semantics, and that could be just folded into the critic.
Yep.
Which is like black boxing.
There
are some questions in the chat. Osbert, should I try to go through these? Or I guess Michi might have already answered.
He answered most of them. I didn't keep track of every single one of them, but I think the last one maybe is not answered yet. So
Okay, is the breaker encouraged to break programs in a way that the fixer can't fix? Yeah, so the short answer is no. There's nothing adversarial going on here. The main goal is to get the breaker to generate realistic code, not necessarily hard code. I think it's, in some sense, it's actually quite easy to generate code that's maybe hard to fix and maybe even impossible to fix, but that wouldn't necessarily help kind of on average the repair fix kind of realistic code. One thing, I mean, maybe one connection here is that, which I guess is hinted at this comment, is that there is a notion of adaptivity here. The synthetic code that's produced maybe is actually an easy distribution, and like in kind of these adversarial settings, what you really want is to cover the cases that are not so easy. And in our cases, the cases that are not so easy are, just to the kind of the real code that didn't get fixed the first time. But maybe there's some kind of more general principle of you can do some sort of active selection of inputs. This might be useful, especially when you don't have as much kind of bad code to begin with. You have to kind of be efficient on how you use it.
I had a question about, I guess at the end you were kind of pitching it as I like the self-supervised learning aspect. And I guess in traditional self-supervised learning, it's usually kind of predicting some other part of the code, whereas here you're making use of the compiler to generate labels. So I was wondering if you had any comparison in like to a more traditional, like how does this compare in terms of how well it works to a more traditional self-supervised learning strategy?
Yeah. I guess I'm using self-supervision a bit broadly to mean anytime you have found data and you can construct some objective. I think it is different than a lot of the self-supervised learning you see in NLP, or I guess, which I'm more familiar with, which is you don't care about the objective to the task at all. You're just using it as a means to learn better representations, and then you're going to use these representations for some task. Here, the self-supervised objective is actually the task you care about, perhaps with the wrong distribution. You actually want to fix code, so you're breaking code and fixing it. But one thing that I think would be a pretty natural boost to the system is take a bunch of code, train like there's these models on like BERT or GPT that are trained on code, and those could be used to pre-train up any of these models. And probably that would work, I'm sure that would work better because you're starting off from a kind of a deeper, richer understanding of at least programs at some level, rather than having to start from scratch here.
Yeah, that makes sense.
Yeah, and there's reasons to do that. Like, I mean, running compilers is not fast sometimes.
Yeah, I had just one more kind of more abstract, or yeah, in terms of how you see this tool being used in practice. I guess like one challenge I imagine is that if a student is actually looking at these error messages, then there's no guarantee that these proposed repairs, and there's no real guarantee that your repair is correct, then it can actually there's kind of a high cost at making mistakes. And I'm wondering if that's something you had a sense, like if you were to think about actually deploying this in practice, what kind of a setting it would be useful in, and what maybe additional challenges need to be addressed to get to that point.
Yeah, I mean, I do think that there's some work, kind of HCI work, to figure out how to actually use this technology. I think that one way you can think about it is like autocomplete. It's offering you suggestions which are not necessarily solving your whole problem, but they kind of make your life a little bit easier. So I know the student case is a little bit complicated because depending on what you want to teach the student, and having the most expedient way of actually having the students synthesize a program is maybe not the most pedagogical thing to do. So that's a little bit more complicated. But I think there are a lot of cases. I think there's maybe the sweet spot, at least given what we've built and the current technology, is fixing kind of careless programmer errors. It's like, okay, you're just typing and you miss a parentheses, and the IDE should just like kind of fix that for you in some ways. And this is not meant, at least right now, meant to be like fixing kind of deep, subtle bugs in your code. And this is more fast, kind of real time. Let's just kind of get going and make sure you're not being dumb kind of things. And maybe I'll just get back to kind of Martin's original point. I think there's this trade-off which we actually thought quite a bit about, depth versus breadth, right? And we've been leaning a bit against the breadth angle because it allows you to have this tool, for example, work for all languages, all linters, compilers, whatever black box. There's kind of this generality that you get for free if you're just kind of black boxing things. And that I think has a pretty nice utility because like you're in some IDE, you might be writing LaTeX, and this could be useful for helping you with annoying LaTeX errors, and those compiler errors are like, they suck. So I would be very happy to have something that fixes my LaTeX errors for me. And I think if you wanted to have a more like semantic approach, it would just take a lot longer. Like this, it's just so cheap. Like you just grab some LaTeX and you grab the LaTeX compiler and then you just like have some system. And so it's not a replacement for the kind of the deep program analysis where you spend years building a model of semantics of C and you analyze it. It's kind of operating in a very different regime.
Right. Yeah, I guess what I was, or my concern is that, if the model is even like only 90% accurate, that's pretty good in terms of ML, but, then 10% of the time it might just be kind of changing my code in a wrong way that introduces new errors. I don't know if that's
So the interface has to, this is where I think the user expectations comes in. Like autocomplete, Gmail suggests things which are often wrong, and I don't accept them because I know, what's going on. I know what's going on, and I want to just reject that. I don't think that the program should be doing program repair like on your code base behind your back and committing it. I think it should always be, in this case, interactive. And at least the cases where you look at this repair and it's like, oh yeah, well, duh, I just missed a parenthesis or something, seems relatively safe. Now, as you expand the scope of what repairs are possible and what you can do, yeah, I think you're going to run into cases where the automation might go beyond the ability for someone to like kind of think quickly and accept a repair or not. But I'm not sure if it's I don't know. I mean, I'm not sure it's that much worse than kind of the average rate of programming errors. I mean, I think it's maybe a different type of error, but I don't know. Programmers are pretty not good anyway.
Yeah, I think that makes sense. But...
Hey, Percy, I got a question for you if you're up for it. So, there's this saying way back at the beginning of the whole latest boom that we were promised flying cars and all we got was 140 characters. And that sounded like a pretty bad deal, but now it looks like the 140 characters may have, oops, I guess I didn't see that person with their hand up. I should probably let that person get us their question first. I'm sorry.
Let's see who has their hand up.
Evan, you
I even forgot my question because it's been a while.
All right, I'll ask my my question while you remember yours. How about that?
You go first. Yeah.
Is that okay?
Go
All
for it.
right, sounds good to me. So anyway, at the time, everybody said, yeah, we got a horrible deal because 140 characters, obviously it's just some chump ass trivial thing. But now it looks like it's got bigger impact than flying cars would have, and that impact isn't necessarily positive. So here's my question. What's the potential transformative breakthrough, transformational breakthrough you see coming from this? And is it going to be good, bad, or indifferent? Or there's no transformational breakthrough on the horizon that you can see?
I mean, I will speak more broadly for ML for generating code here, for example, using things like GPT-3. I think that, well, I'll talk about the bad things I could see, since it seems like implicit in your question, maybe that's what you're asking for. You could imagine a world where programmers are just like generating code that they don't understand. I mean, I think that's the biggest risk. They just generate. It's easy to generate more and tons of it, and it's low quality, and it's copy paste spaghetti code, but it kind of passes some like basic sniff test, and that's probably not a great place, to be.
I mean, arguably that's where we are right now.
That's what I mean, but this is going to make it worse, right? People are taking Stack Overflow, and but now, at least right now, you have to like go to Stack Overflow and you have to copy and paste. Where now you don't have to, you just press tab and then you get your Stack Overflow stuff, and that's just gonna potentially be bad. Now on the good side, obviously this could, you can frame this in many ways. You can say it's democratizing the ability for people to be able to produce functionality on and tap into the power of computing and whatever. So I think there's definitely merit in that. So I think maybe I think it may be worth thinking about how the underlying technology should be deployed into particular products and use cases. I mean, I don't think you can stop people from. I think it's very, very hard to stop people from generating bad code and having bad programming practices. I mean, if you have any ideas, let me know. But so I can see both sides of it.
Yeah. I mean, I'm just taking the long view, and back in the 70s and 80s, people worked on this problem. They thought they were just never going to have to write any code ever again. And now it looks like we're back to writing bad code and maybe trying to fix it up a little bit. It's like this huge retrenchment, just some complete destruction of the grand vision of what the future was going to be like. Maximum dystopia.
Well, I think the key maybe is to have like sharp boundaries. Like in your little play space, you can do whatever you want. But let's get the contracts right. Like you're not going to let your code like seep into some other larger ecosystem. Like for example, I don't know, if you're doing some like random scripting to process some data, and the output, and maybe you just need to get the job done, then fine, just like hack around, and people do this and it's totally fine. But if you're building any sort of architecting some bigger system, then obviously you need like good abstractions, you need code to be like proper design. And right now we don't have the means of at least the type of technology where we're generating tokens is not amenable to that. I do think there is a place where ML could be useful for even those higher level design decisions as well. But those are like much harder to set up. You can't just like download some code and just point a neural net at it.
I'll just make one last comment, then let everybody else can. I mean, at some point, we got to dream big dreams and have big aspirations. And this seems like, it's like saying, well, I can't have ice cream, so maybe I'm stuck with, spinach night or something. Anyway, you see what I mean, right?
I agree with dreaming big dreams. I'm not sure what dream you want to dream, but
I want all the code to be magically there and I don't have to do anything.
You want all the code to be magically there and you don't want to do anything.
Yeah. I mean, okay, so let me give you an analogy. I go to McDonald's, I got to tell them what I want. I go to a restaurant where I'm paying $1,000 a plate. They tell me what I want. I don't have to do anything. Why can't I have the $1,000 a plate restaurant for my code system?
I don't know if you're trying to troll me here. This is,
Come on.
I mean, if you have no preferences, I can give you some code. Like you don't have to tell me if you don't care what it does. I'll generate some code for
The
you.
whole point of the $1,000 restaurant, $1,000 plate restaurant, is they expand your concept of what's possible and gives you things you couldn't imagine yourself.
Yeah.
Anyway, it sounds like, yeah, okay. You see what I mean, right?
Yeah, no, I understand. I mean, but I guess the analogy of that would be, you have some system that's better than a like a beginner programmer. Right?
Better than the best programmer in the world.
But just bear with me for a second. I think already we probably have the means of generating things that an average of a beginner programmer can't proceed. It's like, oh, well, that's a pretty cool idiom that actually gets these test cases right. So I think I would argue that we're already doing that. I mean, even the fan, maybe you're impressed by this $1,000 meal, but maybe the food critic, in SF is not. So they're not expanding there. You need to pay $10,000 for that. So.
Okay, whatever, right? I'll take $1,000 meal for now.
But I mean, I think one of the things with program synthesis is that it's because you have this separation of like what from the how. I think it's quite easy to surprise us and show us like better things. Like even with
really have that separation though, right? Because everything you've got is somebody else's how.
Okay. Well, it's all turtles all the way down, I guess. But I mean, maybe from another, like certainly in language, like generating language models that generate text. I mean, you see a lot of things which I think normal people wouldn't generate. Like if you try to write a story with GPT-3, like you'll generate stuff that at least I couldn't. I mean, maybe for people who are actual writers, they wouldn't be impressed, but
yeah,
the type of language. So I don't know. I mean, I think the data-driven approach is, well, there's two things. Like, how do you get your $1,000 meal? You either tap into enough data where there's some data that is like kind of interesting and surprising to you, and you don't even need to do anything new. You just need to retrieve it. And the other is that you have a well-defined enough objective function that now you can synthesize something that you hadn't seen before.
Okay, so yeah, I mean, I think we should probably wrap up soon. I do see one or two other hands up. I don't know if
I need my question answered.
Okay, do you want to?
Yes. I have two questions. The first one is, it seems to be a kind of tension of like some kind of the RL signal where you are trying to get the compiler to be happy, and there is a kind of a naturalness signal of some almost like fluency, right? Whether your fixer generate code that somewhat like makes sense. Like either, I guess like typically there's like some term that can like extrapolate between the two, like how much fluency you want or versus like how much get it past the compiler you want, right? Is there like a way to make that trade somewhat like explicit in the system you described? Because now it's kind of all rolled up together. Like either like a parameter where maybe like a developer can tweak, be like, oh, you just get it past the compiler. Like I don't care how crazy you make it or make it like look more normal.
Yeah, that's a good question. Well, right now, I guess there's the fidelity to the inputs, and then there's like the whether it passes the compiler. Right now, I mean, passing the compiler is a hard constraint, which means that it in some sense has infinite weight. I suppose you could imagine saying like, oh, okay, I just need to generate something that maybe it doesn't compile completely, but it's like kind of closer to the original.
Yeah, like for LaTeX, there's like some warning, right? Like maybe you like don't care.
Yeah. So you can incorporate that into the critic. The critic can give you like, right now it's either 0 or 1, but you can give you something in between. And there are reasons why you might not want to go all out to try to get it to compile. Maybe like fixing something that at least moves you towards something that's more compilable would be useful.
Okay, yeah, no, I think that's awesome. The second question I think is more kind of open-ended. Like, if you want to humor me, I think this is totally like maybe also derailment trademark, but like, no, like I've been messing with like GPT-3 for a bit. It can do like a fairly simple form of semantic parsing, right? Like if I say like, what is 2 + 5? And I give it like in a prompt, like 2 + 5 as like a string. It can do like some form of that. And you are like the god of actual semantic parsing. So like, how do you view this? Like, how do you think about this thing? I mean, you must have thought about it. I just want like your general utterance in that space. I think that'd be really informative.
Yeah, I mean, GPT-3 is certainly quite surprising and impressive in many ways. And a lot of like, it can zero shot or a few shot a lot of things. I think it's still alone doesn't really solve, the semantic parsing or any sort of program synthesis problem to high accuracy. Like the impressive thing about GPT-3 is its breadth. Like pick any random task, you can just stand it up in like like 10 minutes and get like 70% accuracy. But going from 70 to like 90, you like hit a wall soon. Like you run out of the, you need more examples, and even if you had more examples, you can't put them into the buffer. So yeah, so I think it's not really a full solution yet, although it does improve things, and there are problems where it does like less in code, but maybe in natural language, like QA problems. Some QA tasks it just kind of nails surprisingly well. But yeah, I think any ML work that involves kind of neural models and data, I think should really probably think and contextualize with respect to GPT-3, just to at least make sure GPT-3 isn't solving the thing that you're wanting to do.
Yeah, so like this, sorry, I'm taking more time, but like the tiny code fragment that you're mostly interested from natural language query, right? So like kind of like what's the weather, or like like it seems if you prompt it with somewhat the right prompt, like it kind of do the right thing. It's like almost there, but like you said, it's probably only 70% that's good.
Yeah.
So like I'm not. Yeah. So like
there's a recent paper from Semantic Machines that explores use of GPT-3 to bootstrap semantic parsers.
Okay, maybe
it's on archive. You can take a look at that.
Okay.
It's certainly not trivial.
Okay. No, thank you so much.
Sure.
Okay. Are there any other quick questions? Okay. Yes, I guess we're quite over, so we should probably wrap up. Thanks, Percy, for the great talk today. And thanks, everyone, for joining. And I'll see you all next time.
Yeah, thanks for the lively discussion, everyone.
Yeah. Yeah.
Thanks.